Over the past few months, my group and I have been tasked with researching the differences between Euclidean and non-Euclidean geometry. More specifically, we've been asked to calculate a way to find the difference, the distance between 2 points on a sphere, or in this case, 2 points on the Earth. We hope that this short presentation can give you a helpful insight as to what we've been doing.
I'm going to start our project today by explaining the basic background information that we need to be able to build upon later to ultimately answer our project. To begin, we need to understand why the shortest route between our 2 points appeared to be a curved line on a 2D plane instead of the straight line route that we'd expect to see. As you can see on this image, the red line shows a great circle. And the great circle is a theoretically straight line which will divide our sphere in half. The most common example of this is the equator, even though there are in fact infinite amounts of great circles on our sphere. A geodesic is 2 points A and B on a great circle, which the arc constructed between them will give the shortest route from A to B. Just from these two definitions, we can see how our initial question was true. However, we wanted to know why the shortest route between these 2 points was in fact a geodesic. To help explain this, we link this to a relatable situation. If you have ever been so bored on a flight that you've resorted to staring at the in-flight map, you would have noticed your plane to be taking a similar route to the one shown in blue above. Now, the majority, I'm almost certain, would see this and then resume trying to go back to sleep, taking no notice, whereas we questioned why we'd take this route and not take what appeared to be the shorter route of the black line. Now, I'm sure you'll all be glad to hear the solution to this is fairly simple, and the route you are seeing in blue, when scaled onto a 3D map, appears to be the shorter line, as the flight you are seeing, as the image you are seeing in flight is on 2D, and to nobody's surprise, the globe is actually 3D. And when it is on a 3D image, you can clearly see how the blue line appears to be the shorter route, and the black line unnecessarily takes you all the way around the globe.
So to start understanding this, we need to go all the way back to the mid-3rd century BC, when a famous mathematician named Euclid, who you may or may not have heard of, was living. But actually, very little evidence exists that tells us anything about his life. In fact, some historians actually believe that he wasn't even a person. He was a group of people who, together under the name Euclid, authored this book, which you also may have heard of. Euclid was known as the father of geometry because the elements is, well, Wikipedia defines it as a mathematical treatise, a collection of postulates, propositions, and mathematical proofs. There's 13 books within it, and they all contain the absolute basics of the geometry that we know today, including this. Now, these 5 postulates, or axioms, which means a statement that is regarded as being self-evidently true, so there's no challenging it, it is definitely true. They all seem quite simple at first. These are what Euclid is very famous for. However, as you read down and you see the 5th one, it seems a lot more complicated. I have a hard time even reading it, so I'm not going to. But Euclidean geometry, the definition of it, is geometry that satisfies all 5 of these axioms. However, non-Euclidean geometry is where it doesn't satisfy the 5th postulate, and that's what Jake's going to explain now.
One way the postulates can change is if we change the curvature of the surface we're performing geometry on. Euclidean geometry, for example, is performed on a plane. There is no curvature. Since the Earth is spherical, not flat, as I hate to break it to you, there is curvature. It has positive curvature, and this changes some of the axioms. Most notably, the 5th one. Here is a rewording of the 5th postulate called Playfair's axiom, for which we have a useful demonstration. This, however, is false on the surface of a sphere, and I have a handy globe to show you why this is. This blue line here is the equator, as mentioned, a great circle, dividing the sphere in half. If I want to put a point on anywhere in the sphere, say here, if I then want to draw a line, a great circle, I have to draw it through its antipodal point, meaning its opposite point. You may notice this will always be on the other side of the sphere, separated by the great circle already drawn. So if I'm to draw a line through it, it's always going to intersect this line, meaning there are no parallel lines on the surface of a sphere. This axonomial difference leads to drastic differences in properties of shapes or other things on the surface of a sphere, which our next speaker will talk to you about. Here quickly, before that we do that, is a quick table which shows you some of the differences of the other cubes.
Okay, as with any other area of maths, there is unfortunately actual maths involved. And there's quite a lot of it. My task during the EMC was to decipher all of this and actually make it useful, because at the moment it's just a complete mess. And I managed to narrow it down to perhaps the most fundamental basics of spherical geometry. Now, luckily for you guys, I don't have enough time to go through any of them properly. But I would just like to highlight one of the formula. That's the top one, the area of a spherical triangle. But before that, I've been told that I should probably clarify what radians are. So really quickly, consider the equation 2 pi r. That's the equation that tells you the length of a circumference on a circle. Now, a radian is a measurement of angle using pi. And the equation tells us that we can fit 2 pi amount of radiuses, 2 pi r, around a circle. If we take one of those radiuses and look at the angle that the arc creates, that is one radius. In half a circle, you can put pi of those radiuses, through in a little bit. That's pi radians. And in a full circle, you can fit 2 pi. That's 2 radians. And so we can derive all the normal angles that we know using degrees from these. 2 pi is 360 degrees, pi is 180, pi over 2 is 90, and so forth and so forth. So allow me to pose to you a question, and I put that up way too early. What are the sum of interior angles in a spherical triangle? Well, here it is. Bit too early, I was going to shock you with it. But perhaps the most surprising part about this equation is that the sum of interior angles is not constant. It's not some number like it is in Euclidean geometry, 180 degrees, or pi radians. In fact, it can never actually be pi radians. There's always more, because you can never have a zero area. But what you can have is you can have a close to zero area. And this is where a pretty interesting definition of the sphere comes from. Well, more of a classification. A sphere is a topological manifold. You can ignore the topological part. I just put that part in to sound a bit clever. The word of interest here is manifold, which means that it locally resembles Euclidean n-space. And in the context of this presentation, it means that on a very small scale, on a human scale, if I drew a triangle on the floor right in front of me using tiny little meter-long geodesics, then the area in comparison to the Earth will be negligible. It will be almost zero. And so, using this equation here, we can see that the sum of interior angles is basically just pi radians, 180 degrees. A little bit more, but more or less. And that's where the idea of local resemblance comes from. But when we're calculating distances between 2 points that are really far away, for example, Tokyo and London, it's really not local at all. And so we need a way to calculate these distances, and using all of these equations here, we need a way to calculate that much more efficiently and with a greater accuracy, which Matt has been working on. Thank you very much.
Cool. So calculating distances on a bit of paper is pretty easy. You whip out a ruler, you put it down, you say, oh, that's about 5 centimeters. On a sphere, however, it's slightly different. You could have a tape measure, maybe, sort of wrap it around and try and get a good estimate. But that becomes really difficult when you're working on the scale of planets, unless you had a really, really, really long tape measure, which is just impractical. So to calculate the distance between any 2 points, there are a couple of mathematical formulae we can use. But first we need to know what form these points are going to take. And on the surface of the Earth, most commonly, this is in longitude and latitude. So these are measured as a value of degrees, east and west, and north and south, and is most commonly used in seafaring and naval activities. And with these degrees, as you go to an ever-increasing amount of decimal places, you can express any point on the surface of a sphere. Now, to the type of coordinates we're most familiar with is the x, y, z, as presented there, with which you can express any point in a 3D space. And these are slightly more easy to work with, so what we need to do is convert latitude and longitude into these Cartesian coordinates, as they're called. And we can do this using this diagram. So, as you can see, we have the x-axis coming out through a point which we will call 0. in terms of longitude and latitude. On the Earth, this is on the Greenwich Mean Time zone line at the equator. And from there, we can pull out these two triangles, which I've drawn down here. And the angles theta and phi. Theta is just equal to the longitude, how far east and west you are, and phi is 90 take away the longitude, which is how far north or south. Now, using trigonometry, we can gain these equations over here, which we can use to convert directly between the two. Once we have those, we can use Pythagoras' theorem for 3D spaces. So the difference in the x-coordinates, the difference in the y-coordinates, and the difference in the z-coordinates, each squared and added together. The square root of this will give you the exact distance between any 2 points, and we can use that to calculate the angle at the center of the sphere, and from there, the length along the sector, which will give you your distance between 2 points at any point on the globe. We have a long list of references there. They're also on our poster. Don't worry if you want to look at them. We'd like to massively thank Dr. Anthony Galton for setting this task for us. It was really interesting to research. The maths was really cool. And also the team of university students who've been doing a very similar project alongside us, who've helped us out with some of the more abstract parts. Thank you very much for listening.